Hello, good morning. It's Dr. Berry here. Just wanted to conclude our discussion with a review of hydrostatic forces on a submerged plane surface. And this is a review of the engineering necessary to apply to analyze, to understand the distributed loads on an inclined surface beneath a fluid. We talked about how we needed to find the magnitude of the equivalent force F sub r. And we did that by looking at the pressure at the depth of the centroid, y sub c. We also wanted to find the location to the line of action of that equivalent force. And we identified that location with a parameter known as y sub r. We also needed to now to apply the equations of static equilibrium, being the summation of moment about a point is zero, summation of forces in some x direction is zero, and summation of forces in the y direction is zero. That gives us three equations and three possible unknowns to determine, to ensure that the problem is indeed at static equilibrium. And also wanted to pay attention to understand that although we found the value of F sub r by determining the pressure at the centroid, we do not locate F sub r at that point. We must locate F sub r at the location known as the center of pressure, y sub cp, also known as y sub r. We also understood that in our class, we will primarily be looking at geometries that will involve a rectangle or a circular geometry. And we have, and the parameters that we'll be using is known as the second moment of inertia about the centroidal x-axis, which is 1/12 BH cubed. And where the base is the depth into the board, and where A is the length of the plate along the y-axis. Of course, for a cylindrical or circular plate, IXC is equal to IYC because it is symmetrical. And that has a relationship that is equal to pi times the radius raised to the fourth power divided by 4. Of course, for a symmetrical geometry, the second moment of inertia about the XY axis is 0. And second moment of inertia for the circular plate IXYC is also 0 as well. Now we're going to apply the math, but it's actually is preliminary math, baby math, I call it, because it's algebra and trig. The engineering part is easy. We have to basically apply a little math and let the math do the work to show how the engineering is applied to our problem. The engineering is easy, as I said. F sub r is simply found by looking at the product of the specific weight, gamma sub f, times the distance from the surface vertically to the centroid and times the area of the plate. The line of action of the force y sub r is found by looking at the combination of knowing the value of y sub c, which is the distance to the centroid, is measured parallel to the plate, plus the ratio of IXXC divided by y sub c times the area. Now, it's important, and this is probably one of the more important slides, actually, because it comes down to understanding these definitions. The value of y sub c is measured parallel to the plate from the free surface, and it does not matter. It does not matter if this plate is partially submerged or completely submerged, or if there's a volume of water above the plate. Y sub C is always measured from the surface along the axis of the plate to the centroid, to the centroid of the area. So this may be, say, the centroid. Y sub R is always measured from the surface along the axis of the plate to the line of action of the resulting force. No deviation. This is always the case. And the value of H sub C, though, is measured from the surface vertically to the location of the plate's centroid. Understanding these definitions is the key. This is the key to understanding how to solve for the forces, how to solve for the find the value of the line of action of that force for any geometry that is submerged within a specified fluid. So it is the understanding of these definitions that will help you that is necessary to help you apply the engineering. And of course, understanding that F sub R, which is the resultant of my pressure force, is always perpendicular or normal to the plate. It's always perpendicular or normal to the plate. So let's look at this particular geometry. I have a 200-pound gate that is 10 feet wide. So that's the depth into the board, 10 feet wide and 5 feet long here. And it's hinged at point A here. The gate is held in place by a brace that acts normal or perpendicular to that gate here. And so this gate has a weight component. And that weight, of course, is acting at the centroid. And so I want to find the magnitude of my resultant force and also find the hinge reaction forces at point A. Of course, I will have F sub R that will always act perpendicular to the plate. And this will be strictly a function of applying a little bit of geometry and trigonometry. And the gate, of course, makes an angle to theta with the called this the x-axis. And so we have angles of theta and phi that we will also need to find. So the first question on every exam, on every quiz, will be draw a complete free body diagram of the gate and show all forces, show the assumed coordinate system, and indicate the definitions of y sub r, y sub c, and h sub c. Because it's understanding the free body diagram and understanding the definitions of these parameters that will drive you toward the solution. This will start you down the right path. If you do not understand the definition of y sub c, y sub r, and y sub c, if you do not understand the necessity of having a specified coordinate system, then the engineering cannot be applied, and it doesn't matter about the engineering. So this will be the first step along the path. Follow the path. Very simple. Follow the path. Follow the path. Follow the path. So let's look at this problem. If I look at a free body diagram of the gate itself, this is my plate. This is the centroid. This is F sub R. F sub R is normal to the plate, acting at an angle theta. The brace is acting at an angle phi to the x-axis, and this is and the brace is acting normal or perpendicular to the plate. And we have hinge reaction forces, AX and AY. And it does not matter. It does not matter. Does not matter which direction we show for AX and AY. AX can be going to the right or to the left, or AY can be going up or down. It does not matter. And also, we have to show our assumed coordinate system. Say this is X or Y, but it doesn't matter which direction I show as a plus X or plus Y. I can also show a coordinate system that maybe would look like this. This is X, and maybe this is Y. Or maybe I have a coordinate system, this is plus X, and this is plus Y. The important thing to understand is that there is no standard coordinate system. The laws of physics and nature and God applies to any orthogonal coordinate system. If you're located on the space shuttle in the middle of the delta quadrant, there's no X, there's no up or down or right or left because you're not influenced by gravity. And so there's no assumed coordinate system. So I want you to understand that the laws of physics apply to any orthogonal three-dimensional coordinate system. So that's why it's important. It's important. It's important to show me. Important to show me your assumed coordinate system. So I just want to make sure that it's absolutely perfectly clear and there's no deviation from this level of expectation. So let's look at the value of H of C. H of C is always measured vertically downward from the surface of the water to the centroid of the plate. And of course, my weight component, mg, also acts as well through the centroid as well. I know that the engineering is simply F sub r is equal to gamma times H of C times the area of the plate. Let's first find the angle theta and also find the angle phi. From geometry, I know that theta is equal to the arctangent of 12 over 5. And phi from geometry is 90 minus theta. So theta is 67.4 degrees and phi is 22.6 degrees. Now, we also want to find the vertical leg of this triangle. So we know that the as measured, this distance g is measured from the tip, measuring straight down to the x-axis, say. So g is equal to L times the sine of theta from trig, right? Because the sine of the angle theta is equal to g, okay? The sine of theta is equal to g over L. So g is L times the sine of theta. Once I know the vertical height, which is important now, once I know that the vertical height from the tip to the base, then H of C is simply g over 2. So H of C is then would be 5 times the sine of theta over 2, or 2.31 feet. So now I have all the information I need to find the resultant of my pressure force. F sub r is gamma times H of C times the area of the plate, which is 10, which 10 is the depth into the board, times 5 is the length of the plate, 5 feet, which is here, which is equal to 7,207 pounds force. So the engineering part is easy in terms of having a single expression, a single equation to find the value of F sub r. but we need to understand our geometry, understand the definition of H of C, and be able to apply some baby math, trig, and algebra to determine the correct values of those parameters used in my engineering expression for my resultant force. So you see here, this is foot cubed. You see here, this is foot cubed, and the foot cubed cancel out here, here, and here. So we end up with a pound's force as our unit, of course. So now the second step, step two along the path. So there are no other options. Step one, find the value of F bar. Step two, find the location of my resultant force, known as either Y sub R or Y sub P. And just make sure that we understand that it's always measured from the surface parallel to the plate itself. So we have an expression that we use to find the value of Y sub R. So this is the engineering. The engineering is easy. Engineering says that Y sub R is equal to Y sub C, which is the distance to the centroid, plus IXC over Y sub C times the area. So if Y sub C is measured along the axis of the plate and it's the distance to the centroid, then Y sub C is L over 2 or 5 over 2, which is 2.5 feet. So I know the value of Y sub C because I understand the definition of my of that parameter Y sub C. And so we have Y sub C plus 1 over 12 BH cubed divided by Y sub C times the area. I know that the base is the distance into the board, and that's 10. I know that the length is 5. So therefore, Y sub R is equal to 3.3 feet. And Y sub R is always greater than Y sub C. Okay, this must always be true, that the distance to the line of action of the force is always greater than the distance to the centroid. So therefore, the line of action of my force is always below the centroidal location. So I have this force that's acting on this gate. It's a value of F sub R. And this is some distance of a Y sub R. So now I know the location of F sub R. I know this distance here. I know the value of Y sub R. And I know the value of Y sub C. Okay, so now I need to find the 3 external forces acting on the gate. The 3 external forces would be the hinge reaction forces, AX and AY, and also find the force of the brace, acting on the gate. These 2 angles are the same from geometry, theta and theta, here and here. So I need to take the summation of the moments about some point, any point. I need to take the summation of forces in the x direction, and I need to take the summation of forces in the y direction. So normally we want to take a moment first about some point. We can take the moment actually about any point, it doesn't matter. But if we're smart about our choices, our equations become simpler. For example, if I choose point A, I know that AX and AY are two forces that go through the point. So if a force goes through my moment point, those force components, they do not have a moment about point A. And so that may make sense because they are unknown components. I have three unknown forces, AX, AY, and the force of the brakes. So if I choose point A as my moment point, then I can eliminate two of the unknowns within my parametric moment equation. So let's do that. I choose to take the summation of moments about point A, and I assume that a counterclockwise rotation is positive. You must show me this. You must show me that you understand that I must indicate which direction is a positive clockwise moment and a counterclockwise moment. Because otherwise, how can anyone check your work? No one can check your work if you don't tell them which direction is plus or minus. So let's proceed and take the moment of all the forces acting on a gate about a single point, point A. So, but first let's review the definition of a moment. A moment is defined as the product of the magnitude of the force times the perpendicular distance to the point of rotation. So it's the perpendicular distance, and the word perpendicular is what's important there. It's the perpendicular distance between the line of action of the force and the point of rotation. So if this is the force of the brakes, this is the line of action of that force. This brace is going to act perpendicular to that gate. So I want to find so the moment is the force times the perpendicular distance, between the line of action of the force, okay, the perpendicular distance between the line of action of the force and the axis of rotation. So, and this force F sub B creates a counterclockwise rotation about point A. So that's plus F sub B times its moment arm, which is L. L is the perpendicular distance between the line of action of the force F sub B and the point of rotation. Now, if I look at the weight component, this weight component is going to create a clockwise rotation about point A. So the weight component is m times g, and it creates a clockwise rotation about point A. And so therefore that means that the moment is a negative moment. Now let's look at the moment arm. If this is the line of action of the force, and this is perpendicular, then this distance here is the moment arm. This is the moment arm for the weight component of my forces. And so this distance here is going to be equal to, if I take the cosine of the angle is going to be equal to this distance divided by L over 2, because this distance here is equal to L over 2 because the force acts at the centroid. So the moment arm is equal to L over 2 times the cosine of theta. Let's look at F sub r. F sub r is also acting normal to the gate. And so its moment arm is this distance here. This is the moment arm. The moment arm for the reactionary force F sub r. Okay. So what is the value of the moment arm associated with F sub r? Well, I know that this distance here is equal to y sub r. And if this distance here is equal to L, then its moment arm would be L minus y sub r. And because it creates a clockwise rotation about point A, this is minus, and that's equal to 0. So therefore, as you can see, I have one equation and one unknown for the value of F sub B. So F sub B becomes then mg times the cosine theta times L over 2 plus F sub r times L minus r over L. So this is the parametric equation to find the force of the brace acting on the gate in terms of the weight, in terms of the angle theta, in terms of the length of the gate itself, and in terms of F sub r. And as you can see that, let's say that as theta goes to 90 degrees, the cosine of 90 degrees is going to be 0. And so if it's 90 degrees, then there is no force of the brace acting on the gate, and the F sub B is simply would be equal to F sub r times 1 minus y sub r over L. Okay. Likewise, if theta goes to 0, which is an odd angle, the cosine of theta, of course, goes to 1, and then so the force of the gate would be equal to m times g times L over 2 plus F sub r times L minus y sub r over L. So looking at the parametric equation gives me an opportunity to understand how the different variables interact and how they impact the overall problem in terms of being able to find the value of F sub B. Now, next, I want to take the summation of forces in X and Y. And note here, I indicate which direction is plus and which direction is minus. So I need for you to show me on at this point, to show me that you understand that I must have an assumed coordinate system, an assumed plus direction and minus direction, and to indicate so on your summation sign, because a problem can be, as you can perhaps see, a problem can be a number of pages long, and you must be able to carry that through from step to step. So the summation of forces in the X direction is 0. I know that according to my free body diagram, that A sub X is plus going to the right. Now it doesn't matter which direction I show for AX or AY. It can be plus going to the right or going to the left. All that means is if I solve for it, when I solve for the value of A sub X, if it turns out to be negative, that means that my assumed direction on my free body diagram was just incorrect. That's what that means. Okay. Now, now I would have now I would have then plus AX plus F sub bar times the sine of theta. I must break this force up into X components and Y components. I know that this angle is the same. So this force component here is F sub bar times the sine of theta times the cosine of theta. And this component is F sub bar times the sine of theta. So this is my force triangle for F sub bar sub Y and F sub bar sub X. So therefore then I'd have A sub X plus F sub bar times the sine of theta. And likewise, I must also break my brace component force up into X components and Y components as well. And so I can break this force up into Y components and X components. Okay. And if I do that, I know that this angle here is psi. And this component will be F sub B times the cosine of psi. And this component is F sub B times the sine of psi. Okay, so that's a minus F sub B times the cosine of psi is equal to 0. And once again, I have one equation and one unknown because I know F sub B, I know F sub R, I know phi, and I also know theta. So therefore, I can solve for A sub X. Okay. Likewise, for the summation of forces in the Y direction, I would have plus AY because it's a plus as shown on my diagram. And then I would have minus F sub R times the cosine of theta because this force is negative when I break F sub R up into X components and Y components, plus F sub B times the sine of phi, which is here. Then, of course, minus mg is 0. So this gives me the parametric equation to find the value of A sub y in terms of my pressure, reaction force F sub r, the force of the brace acting on the gate F sub b, and the weight of the gate. Of course, A sub y has to balance the weight. A sub y has to balance the y component of the of my pressure force F sub r. It also has to balance the y component of the brace. Now, of course, the reason why we ultimately need to find the forces acting on that hinge because perhaps we need to use our skills from machine design or solids to determine the stresses in that pin at the hinge location. To determine the stresses in the pin for the hinge, we need to understand the forces that pin must endure. So from a design standpoint, we may need to determine the stresses and strain that pin may see, and also be able to determine, well, how large of a pin I may need and comprised out of what material: steel, aluminum, titanium, whatever. So typically we would need to understand the stresses, pick right material, and also to determine the diameter of the pin. And that's something that we perhaps may have done in solid mechanics and also in the course called Design of Machine Elements. So we have AX, and a Y. Of course, A is a vector. We can determine the magnitude of that force and also determine the angle theta that the force makes with the x-axis. And these are all standard equations from static equilibrium. So if we look at our force triangle, our force resolution, we have broken F sub r up into x components and y components. We've broken the brace force up into x components and y components. Of course, we can always use or express F sub b, the force of the brace, in terms of theta or psi, and the weight component also is broken up into its y component. It only has a y component, but this represents the moment arm. The moment arm for the moment of the weight with respect to the hinge here at A. So now that we have looked at this problem and understand how we would solve this problem for a simple submerged gate beneath the surface, but aligned with the surface. Let's look at another problem. Here we have a gate that also has 9 feet. 9 feet of water above the top of the gate. And so once again, I want to be able to find my value of my reactionary, of my pressure force F sub r. I want to find the value of the hinge reaction forces Bx and By. And this gate sits along a wall, and we say that this wall creates a horizontal F wall. The wall creates a horizontal wall, a horizontal force that is a horizontal force that is acting at point A. Okay, so we want to find the value of my reaction force F sub r. We know that that's equal to gamma times H sub c times the area of the plate. We know that the gate is 5 feet wide. We need to find the value of L. We have a 3, 4, 5 triangle. The sine of theta is equal to 6 of L, or L is equal to 6 divided by the sine of theta, or L is equal to 10 feet. So this gate here, this gate has a length equal to 10 feet. So from geometry and trig. So H sub c, though, we know that H sub c is always measured from the surface right down to the centroid of the gate. So to find the value of F sub r, I need to understand and find the value of H sub c. And note it is still measured from the surface of the water. It does not matter about the geometry. It doesn't matter if it's completely submerged or submerged 100 feet beneath the surface. H sub c is always measured from the surface vertically downward to the centroid. So we need to find the value of H of C. We need to find the value of H of C. Okay. So first of all, let's find the angle of theta. I know the theta is equal to the arctangent of 6/8. We're good there. The center of the gate is halfway between or at elevation of 3 feet above B. Okay, so I know that this distance here is equal to 3 feet. So if the total distance is 15 feet and H of C is halfway from the bottom or at 3 feet, I know then that the value of H of C is equal to 12 feet. And once again, we found the length of the gate. So I know the value of H of C is equal to 12 feet. And this is the area of the plate. This is gamma of the fluid. So therefore, the force is equal to 38,400 pounds force. So the engineering was easy, but we had to apply a little baby math in terms of trig and geometry to find the magnitude of that pressure force acting on the gate. And so this force is acting normal. This force is acting normal to the gate itself. So let's move forward. Okay, so as we move forward, I found the value of H of C. Now I need to find the location of the line of action of my resultant force, F sub r. So I know that to find the value of y sub r this is F sub r, that this distance here is the value of y sub r. So I know the distance from A to the centroid. So I know that this distance here is equal to L over 2. So to find this total distance here, I need to find the value of L1. So I know from geometry that these angles are the same. here and here. So the sine of theta is equal to 9 over L1, or L1 is equal to 9 divided by the sine of theta, which is equal to 15 feet. So the distance to the centroid y sub c would be equal to 15 feet plus L over 2, or 15 feet plus 10 over 2, or 20 feet. So now so I know the distance to the centroid. Okay. So let me just erase this a bit. So if I draw this again, this is F sub r, and maybe this centroid is here. So maybe this distance here is y sub c, and this distance is y sub r. And I know that this distance from A to the centroid is equal to L over 2. So y sub c is equal to 15 feet plus L over 2. Okay. So now I'm good. So now I know that I can find, I know that I have an expression, an engineering expression to find the value of y sub r. Y sub r is measured from the surface along the axis of the plate to the line of action of the resultant force, F sub r. So let's find the value of IXC, which is BL cubed over 12. Of course, the base is always the depth into the board, which is 5 feet, L cubed over 12. So IXC is 417 foot raised to the 4th power. So I know the value of y sub c from the prior slide. Y sub c is equal to 20 feet. I'm good there. So therefore, I now have all the information I need to calculate I sub xc, or I have all the information I need to calculate the value of y sub r. Okay. And so that gives me all the information I need to find the location of my resultant force, y sub r. Of course, if I want to find the distance between F and B, the distance between the line of action of the force and the pin, that would be equal to 10 feet. Of course, 10 feet is the value, would be equal to, well, let me, the 10 feet, of course, is the length of the plate itself. So we have 10 feet plus 15 feet. I'm looking at the total distance from the surface itself, which would be 10 feet plus 15 feet minus y sub r would be the distance between the line of action of the force and the point of rotation itself. That's important because I need to know that information when I take the summation of moments about the point, because I need to find my wall reaction force of P. As I assume that a counterclockwise rotation is positive, I take the summation of moments about point B. And so I see that B creates a counterclockwise rotation about B. So my wall here, which I call P, so the wall force creates a counterclockwise rotation about point B. And so, so that's plus P, and times the perpendicular distance between the line of action of that force and the point of rotation that's equal to 6 feet. Now, my pressure force at F creates a clockwise rotation about point B. And so that's opposite to my assumed direction, which is positive. So that's negative F times the perpendicular distance between the line of action of the force and the point of rotation. And that distance, which I found now, is 4.583 feet. So this gives me one equation, and want to know to find the value of P. And continuing on, as we've done before, we are following the path. We know that summation of forces in the x direction, I have plus bx. And as before, I break F up into x components and y components. I know that this is the angle of theta. So plus F times the sine of theta minus P is 0. So that allows me to find the value of B sub x. One equation and one unknown. Taking the summation of forces in the z direction, I know that I have plus BZ minus F times the cosine of theta. And so therefore, this allows me to find the value of BZ. So this is the parametric equation to find the value of a BZ. This is the parametric equation to find the value of BX. Okay. So now one more problem to solidify these discussions. I have a reservoir with a circular duct or a circular gate and has some distance h. The depth is h, in which I don't know. My diameter of my plug gate is 4 centimeters, and it's located 3 centimeters above the lower right corner of the tank. I know that the plug will pop out if the hydrostatic force exceeds 30 newtons. I want to know the pressure at the bottom of the reservoir. And also I have a manometer now. This manometer has been integrated with this gate. That's fine. I want to know the reading of H on the mercury manometer on the left side of the tank. So I know that F sub r has to be equal to 30 newtons. So the value of F sub r, the value of F sub r has to be equal to 30 newtons. And I know gamma. I do not know the value of Z sub C, which is the distance to the centroid. Okay. Times the area of my plate is the circle, so it's pi d squared over 4. But this allows me though to find the distance of H sub C, or in this geometry, Z sub C, which is fine. What we simply call this, then we simplify down as my axis Z. So ultimately, if I'm trying to find the pressure along the bottom of the tank, I need to find the total depth of the tank. I cannot find the total pressure at the bottom of the tank until I find the total depth of the tank. So I know the value of Z sub C, okay? And I know the value from the edge of my plate to the bottom of the tank is 3 centimeters, but I do not know the vertical distance from the centroid to the edge of the tank. I'm saying from the centroid to the edge of my plate here, okay? But I know that this is the radius is equal to 0.02 meters. I know that this angle theta is the same. This is the angle of theta. So the sine of theta is equal to L over R. The sine of theta is equal to L over R because I need to know this depth is what I'm trying to find. I need to know this depth. So therefore, L is equal to R times the sine of theta. So L is equal to 0.015 meters. So the total depth of the tank is Z sub C plus L plus 0.003 meters. So the total depth now is equal to 2.49 meters. So the pressure at this point is gamma times H. I know that the hydrostatic pressure at the bottom of the tank is not a function of direction. So the total pressure on the bottom of the tank is gamma times H. I have gamma of water is 98 newtons per meter cubed times the distance of the distance H. So is equal to 24,402 pascals. So I know that this pressure here, this pressure on the bottom of the tank along this constant depth, this pressure is equal to 24,402 pascals. Now I have a manometer and I need to find the value of H. Big deal, because I understand the definition of a manometer. Whenever I see a problem with manometer, I'm happy because I know that the definition of a manometer is that it allows me to find a pressure differential. So somewhere in the problem, I need to use my manometer to find a pressure differential. And so I know that it's a mercury manometer. I know that the specific gravity of mercury is 13.55. I know that the specific weight of mercury is my specific gravity times gamma of H2O. So the specific weight of mercury is 845.52 newtons per meter cubed. I want to apply manometry for my manometer. So what's the first step in always applying the point-to-point method is I need to label the points, label the different elevation heights. So this is 1, 2, and 0. So if I start at 1, I know that P1 plus gamma of water times its delta Z, that gets me from 1 to 2. Delta Z is equal to 0.02 meters. Okay. And then from 2 to 0 minus gamma of mercury times H is equal to a P0. I know that P0 is equal to 0 gauge pressure. So this allows me to find the value of H, which is equal to 28.9 meters. So I have applied the law of hydrostatics to the gate, and I've transferred the pressure from the law of hydrostatics along the bottom of the tank. And I've used that value of pressure as the inlet pressure into my manometer at 0.1. Applying manometry, then I can find the value of H on my manometer. A manometer is used to measure a pressure differential. Whenever I see a manometer in the problem, I must always be thinking I must be required to combine the use of my manometer with anything else I'm trying to find. And that concludes my review of how we apply the law of hydrostatics to to understand the pressure forces applied to an inclined surface, and then also just preparing us to understand that we will also be integrating these different concepts into a number of different problems. And that's why it's important to be able to understand how a manometer works, understand the definition of a manometer, understand how to apply the engineering along with the baby math to find and analyze the pressure forces and the and also to find the line of action of that pressure force for a inclined surface. Thank you very much.